4, 7, P of 9, 23, P of 25, and 7, and so forth. P of 300, P of 7. You guys, I don't know, but you guys probably don't understand the magnitude of the difficulty of this problem. To find this formula would be like, well, it's nearly impossible. To be accurate, let's say you found a formula that's accurate for all these guys at 25,000. I literally put 25,055, and somehow I got a formula that gave me this number. For your formula to stay accurate to this guy, then to this guy, like eventually they'll either start messing up or start giving you numbers that aren't prime and so forth. It's just for it to stay accurate to the last prime, which there is no last prime, to stay accurate forever would be very hard. So the magnitude of this problem is like beyond measure. But so
people expect that there is such a formula?
Well, we are kind of confident. Or so I am. I would love for there, but we're not even close to it. We're not even close to it. So we're going to talk about the next best thing. Well, first we're just talking about this little thing. It's just a cool little image. Start with 1, and then 2, 3, 4, 5, 6, 7. Just start going across like this. It's called the prime spiral, or the Euler spiral, so forth. And then take out every non-prime number. Take out every number that's not a prime. And what you'll see is the prime numbers start lining up in diagonal. This right here happens just to be a 7 by 7 grid. When you expand this image to like, let's say 200 by 200, and do the same thing, take out every number that's not a prime number, you're going to see the prime numbers start lining up in spirals, in diagonals all across the place, everywhere. So it gives us a little hope there's some sort of pattern. That's what we're looking for. The Euler spiral is pretty cool. I wish I could have found a bigger image. So formula primes continue. No. This is a algorithmically devised picture. It's not even fatal. It doesn't line up in the exact. And I wish I could have found a bigger image. It's just you see this 19, 7, 23, 47. This next guy would be prime. There might be a guy that's not prime, but again, there's a prime there. And it's just in general, not every single guy would be a spiral. Not every single guy would be a diagonal and would be perfect, but it's just in general, it's just a little pattern that this guy noticed about 40 years ago. It was in the 1960s.
Yeah.
No, it's not almost a formula. It really tells us no more information than, because we already know what these prime numbers are, so we're the ones building this thing. We're just noticing that for some reason they're lining up along this diagonal. There's space right here. What?
Yeah. There's space right here.
Right. But it doesn't really do much in terms of give us new information. It's just it makes us hopeful that there's some type of pattern.
There's gaps in the diagonals.
Yeah, there'll be gaps in the diagonals, and it won't be exactly perfect.
There will be offs.
Because for example, when nature went, when we defined multiplication, and nature went picking the primes, it was almost like a coin toss. Coin toss. Numbers have a probability of being prime. We'll see about this in a little bit.
This is exactly how one approached it.
Oh, I don't think so. Not. He was supposedly he was just in some boring scientific conference, and he was just there, not paying attention. He just started jotting down, doing the little thing, and he just noticed these primes. It's exactly what he did. He just noticed. He went home after the conference and expanded it and saw that the pattern kept going. All these primes were lining up in diagonal, and so next month it was on the cover of Scientific American. Whatever. Eventually, by the 18th century, mathematicians, like I said, practically gave up searching for this Pn, right? That exact prime number, and prime number. They started to think about the next best thing, the prime counting function, which we either know by pi of n, or pi of x. This has nothing to do with the number pi. It's an unfortunate choice, but.